All right, so last month Kevin talked a little bit about RF and agreed this month to talk a little bit about antennas. So take it away, Carl. Kevin.
So antennas. Last week, I want to revisit a couple things. There is antennas are all about wavelength, and so the relationship between frequency and wavelength is this: is there's the speed of light, there's frequency, and there's wavelength. And as I said before, I remember just a couple relationships, and then hold on, I want to set a timer too. Stand by one. I remember a couple relationships, and then I just ratio my way into it. So into what I want to go to. So 300 megahertz is a meter, and 1 gigahertz is 30 centimeters. And so those are the two that I remember. And then if I need to get somewhere, yeah, that's right. So anyway, so those are the relationships I remember. There's also another relationship we talked about last time, which was lambda over 20. And lambda over 20 is the threshold between if a physical piece of conductor is smaller than lambda over 20, it's usually not significant with respect to radio waves. If the physical size gets larger than lambda over 20, at that point it starts to participate in radio frequency events at that the frequency associated with that wavelength. So we talked about before how this was the precision of a parabolic dish has to be accurate within lambda over 20. So that's the threshold. So what do we want out of it? What's an antenna do? What do we want out of an antenna? So it's a interface between guided waves and unguided waves. So and I'll talk about it in both in transmitting sense and a receiving sense. Those are equivalent concepts. There's relationships that translate between both of those. Sometimes it's useful to talk about a particular antenna effect in terms of an antenna receiving something, and sometimes it's useful to talk about it in terms of a transmitting perspective. But they're equivalent concepts, and as I said, there's relationships between the two. So an antenna is an interface between guided and unguided waves. So for example, an unguided wave, these are the crests of a wavelength. You have some sort of antenna, parabolic dish that's collecting that signal, and then it turns into, here it comes into coax. So that's the first thing. So from a receiving perspective, this power comes at you with some sort of power density in watts per meter squared. In watts per meter squared. This receiving antenna presents some sort of area, which we'll call the effective area, to that oncoming wave. And so we've got area times power density, and that gives us a particular amount of watts, the watts coming out of the coax. From a transmitting perspective, we have a power amplifier, and that goes into an antenna. And then this is a transducer between this guided propagation on the coax and the wavelengths in the air. And so in this kind of situation, we think of things like antenna gain, effective radiated power, that sort of thing. So this is the transmitting model that we're going to play with. So there's going to be some sort of power amplifier that's going to be connected to a coax, to an antenna. Inside that antenna, there's this is our circuit model. Inside that antenna, inside a power amplifier, there's a voltage source and a resistor, coax, and then inside the antenna, we want to build a resistor we call the radiation resistor. And any power that gets dumped into that radiation resistor is good power, because it's the power that dissipates gets transmitted into the air. There's also oftentimes a loss component in the antenna, and we don't like this resistor because any power that we dump into this load, into the loss resistor, just gets dissipated as heat. And in an ideal world, we work to have that resistor be the same as that resistor, and that's the matched case. And when we have that matched case, that means the antenna is accepting all the power that the power amplifier is able to deliver to the resistor. So that's our transmitting model.
That's the resistance of the coax cable, right?
No, that is, so if you build an antenna, you build a dipole or something like that, it's a piece of copper wire, and you look at it, there's no resistor anywhere. But when you analyze it from an electromagnetic perspective, it turns out there's a real resistor that shows up on these two terminals right here, and that's the radiation resistance. If the antenna is lossless, that's the radiation resistance. In the radio world, we want this resistor to be the same as the characteristic impedance of the coax, to be the same as that radiation resistor. So that's the match condition. Does that make sense? So if you buy a power amplifier, it'll be a 50 ohm power amplifier. The cable you use will be 50 ohms. And if the person who did the antenna did it right, when you look into the antenna, you'll see a 50 ohm load. And that 50 ohm load is the radiation resistance. But again, you look at the antenna, it's a piece of copper. There's really no resistor in there that you can suss out. That resistor is the model for the power that gets dissipated into the atmosphere or into the ether. And by the way, that's questions. I'd rather have this a conversation than it be me just talking. Does that make sense?
It's resistant to the
So,
frequency.
Say that again?
I think of it as impedance, which is resistant at a particular frequency. So
right, but we
talk DC resistance.
Well, we go out of our way to make sure that this resistor, all these resistors are resistive at whatever frequency we want to work at. And so we like these to be wideband, works over all frequency kind of things. That's what we strive to do. It turns out that we're not going to discuss this too much tonight, but if you build a dipole, and this is around half a wavelength, the impedance looking into that thing is 72 ohms at whatever frequency half a wavelength is. But as you look at it at different frequencies, the impedance deviates from 72 ohms. So what you do is you say, I'm going to operate this thing at whatever frequency is lambda over 2, whatever frequency corresponds to lambda over 2 of the physical size of this thing. And then at that point, it'll be 72 ohms if I've done everything right. But as I move away from that frequency, it'll no longer be 72 ohms. And so the match won't be as good as it could be. And for dipoles, typically the number that people throw around is they have about a 10% bandwidth. So 10% of the center frequency. So if you had an antenna that was working at 100 megahertz, its bandwidth would be about 10 megahertz. That makes sense? All right, let's press on with a different color. So this is the, I want to get rid of this. Okay, so this is the receiver. I'm sorry, we're still at the transmitting model. So we dump power into that radiation resistance, and it gets thrown into the environment. And you'll often see patterns like this. And essentially what we're looking at here is, there's two ways to look at this. Is you can either start at the center of the antenna and walk around it with a power meter, and then at this angle you measure high power, and at these other angles you measure lower power. The other way to look at it is to walk around the antenna, always keeping the power meter reading the same power, but you move farther away to keep that meter to read the same power. So let's say you're reading you set your magic number to be a milliwatt. So you'd read a milliwatt here. Oh, wait a minute. So you'd read a milliwatt here. At that point, I need a different color. as you'd walk along, keeping the power meter at a milliwatt. So you read a milliwatt here, here. So obviously, most of the power is being thrown out in this direction. So this is a high gain antenna. And what that means is it throws a lot of power in one direction at the expense of throwing power in other directions. For a dipole, and most of the antennas we're going to look at tonight are going to be dipoles, and most of the antennas in the real world turn out to be just arrays of dipoles. This is the gain pattern you see on a dipole. If that's your dipole right there, you see a donut pattern. So you take, if it's the dipole is a rod, you take the donut, stick the hole through the rod, and that's the pattern of the antenna. So for dipoles, most of the pattern, or most of the energy goes out. I need a better color. Most of the energy goes out in these directions, the broadside to the dipole, and nothing comes off the top. And there's some nomenclature associated with antenna patterns. Oops. Sorry about that. So there's typically with an antenna that has gain, and in other words, it throws power preferentially in one direction. There's these areas of intentional radiation, which would be over this angle if this is the center of the antenna. And then there's these other areas which are unintended radiation. And some of the nomenclature you'll see are side lobes, which is power throwing out the side of the antenna. There's back lobes. There's nulls looking into those areas. So that's some of the nomenclature. Okay, so that's the transmitting model in a nutshell. So this idea of taking power into a radiation resistor and throwing it out into an environment is a good, strong mental model for a transmitting antenna. Let's talk about receiving antennas. So this is a model for a receiving antenna. So we have an antenna that's sitting in the environment. Again, power is coming at this thing with some sort of, with some sort of watts per meter squared metric. This antenna presents an area to that power as it impinges upon it. And so area times watts per meter squared gives you watts coming out the back end. There's a couple points. So the antenna collects not only the signal that you're interested in, but it collects noise from the environment as well. This can be galactic noise. It could be Gaussian noise created by a natural process. But in urban environments, mostly it's microwave ovens and computers and light bulbs these days. All this stuff is generating noise, and since there's so many of them, they all combine together to represent Gaussian. They look like Gaussian noise, even though they're not Gaussian noise when they first get generated. There's so many of them that they end up looking like Gaussian noise. And there's also a little bit of heat. Again, we're not going to worry too much about the loss of the antenna proper.
So Gaussian noise is a distribution around the frequency that the antenna is designed to receive?
Yeah, so the antenna is sensitive to frequency, and this area changes with frequency. So where the antenna is designed to be a good antenna, this area will be large. As you move away from that frequency, this area can get smaller and smaller to a point where it's not collecting anything at all. So there's galactic noise goes out to a couple terahertz. If you look at the noise plots in the world, so if this is frequency and this is noise power, up at low frequencies where this is say a megahertz, and this is say 10 gigs, it looks a lot like this. So up at very low frequencies, there's a huge amount of noise power coming from the environment. And up at the higher frequencies, it's less. In fact, the noise up here at megahertz sort of ranges, the receivers that people build are called HF receivers, high frequency radio receivers. They typically, in their design, they don't worry about noise performance because this noise is so huge that there's almost nothing you can do in the radio to foul it up, to generate more noise than the environment comes in. In the UHF VHF range, which is kind of right here, 30 megahertz to a gigahertz or so, you can build a system that will add noise to the noise collected by the antenna. So we worry about noise performance when we design systems in these ranges, and actually higher out as well. But up at down at the HF range, we don't worry about that at all. Does that make sense? So we've got a couple things going on. Is the amount of signal and noise collected by the antenna has to do with this area that the antenna presents to the oncoming waveform, and it also has to do with what particular frequency you're at. At low frequencies, the noise in watts per meter squared is a lot higher than it is down here. So this is the receiving antenna model that we built. So this is the receiver, and this is where the signal comes from. So since we're looking to collect FM radio at 101.1 megahertz, say, we model that as a signal generator that's generating that. You'll hear the term antenna noise temperature, and we're not going to get into it too much in this lecture, but we blame all the noise that this antenna collects on this resistor. We say this resistor is at a particular temperature, and you'll hear the term antenna noise temperature, and that's what they mean, is the temperature of this resistor. It's not a physical temperature. This is a mathematical model. So it's routine to see noise temperatures of 10,000 degrees. So for example, up here in the HF range, the noise temperatures are 10,000s of degrees. Down here, it gets to be 290 degrees or about room temperature. These are all kelvins. But from a model point of view, what we do is we blame the noise that the antenna collects on the temperature of this radiation resistor. And that is, if you hear the term antenna noise temperature, that's what they're talking about. So for example, if you have an antenna, a parabolic dish, a Arecibo, for example, that's looking up at cold sky, and cold sky, I think, is 2.7 Kelvin. So the noise temperature of that resistor is 2.7 Kelvin. If you have an antenna that's looking at a TV antenna that's at the top of your house, looking across the city to a tower somewhere that's transmitting TV, the noise temperature of this resistor is in the neighborhood of 290 Kelvin, or about room temperature. So this noise temperature can change all over the place, and depending upon what that is, tells us, do we need to design a system that is low noise? Do we need to throw liquid nitrogen on this thing to cool it down, or what particular design parameter do we need to do? Does that make sense?
So would you need to cool down something that had a high noise temperature or a low noise temperature, like the 2.7? Does that need cooling, or is it the?
You would this would be the one you would cool, because the noise temperature coming into the antenna is 2.7 K, which is cold. If you had it, again, we're not going to get into too much in this lecture, but this receiver also has noise performance, also pumps noise into the system, and you're interested in the temperature of this resistor, which is your antenna noise, is your system noise temperature, and this relates to noise figure and all those other noise numbers you may have played with or heard about. So there's, based upon the design of your system, this has a temperature. And so, for example, if your system has a noise figure of 3 dB, this noise temperature is 290 Kelvin, is how that works out. So, and this is sort of garden variety, easy to do by parts from DigiKey kind of stuff. Is 3 dB noise figure is not difficult to do. This is to get a noise temperature of 2.7 K is heroic. It's liquid nitrogen and carefully designed systems. In the HF case, like I said, this noise temperature is 10,000 degrees Kelvin. So if you have a system here that's 290 degrees Kelvin, most of the noise is coming from your antenna here. And so you can really foul things up before you even get close to, before your system injects a significant amount of noise into your system. So yeah, the Arecibos and things that are looking up at cold things, at skies and stuff like that, those are the things that want liquid nitrogen cooling. Most of the stuff, the HF stuff, and most of the stuff that we deal with, we don't have to deal with that situation. We worry about it. You can get 1 dB noise figure amplifiers, which I'm forgetting the numbers, but I think that's probably about 100 degrees Kelvin. That's not garden variety, but it's easy to get. You pay a little more. Once you get a little bit below that, it starts to get it gets a lot more difficult. And again, these aren't physical temperatures. We're just using these as mathematical models. There's no resistor in the system that's at 290 degrees Kelvin or 10,000 degrees. Okay, we'll press on. So again, from a receiving perspective, this is what the system likes. So this is the gain pattern we talked about earlier. And so, oops. So if your wave comes in this way, and let's say this is, just to put a number on thing, let's say this is 1 watt per meter squared, which is a huge number. Coming into here, coming into the main lobe of the antenna, the power you see coming out of the hose on the back, the coax on the back, will be a particular value. If you come into places that have lower gain, then the power you'll see coming out the coax on the back of the antenna is going to be lower, even though it's the same watt per meter squared coming in this way, because the gain is lower and the aperture is lower. You receive less power. And if you come into one of these nulls with, again, the same power level, power density coming in, you'll see an even smaller amount of power. So this gain relates very directly to the effective aperture of the antenna. And also, I want to be clear, it's not a geometrical thing. So if you have an antenna that's got, say, a meter squared effective area, it's not that you're looking at it at a different angle. That, if you look at a square direct on, you see a meter squared, but if you look at it at a 45-degree angle, you'll see less of that. It's not that effect. It's very much related to the electrical performance of the antenna. So it's really not a geometric thing. Does that make sense? Okay. This is just repeating what I said. This is a relationship between gain and effective area. Keep doing that. So this is just the gain in a particular direction, and this is just the aperture in a particular direction. And they're related by this number. So if you measure the gain at a particular point, you can crank it through this equation and you'll get the effective aperture of the antenna. Like I say, they're equivalent models. They do the same thing. The math all works out. It's more convenient to think of things in receiving sense or transmitting sense sometimes. Oops, hold on for a minute. And some antennas, so if you have a parabolic dish, you can kind of look at that and see that there's this physical area associated with it, pi r squared. And normally there's a relationship between the physical area. There's rough relationships between the physical area of they call these an aperture antenna because you can look at them and see sort of an aperture going on. And so there's an efficiency, which is the effective area over the physical area. And if somebody needs, if you need a number, this is usually about 50%. So there's another kind of antenna you might have seen called the horn antenna that looks a little like this. And so there's this square aperture, and the same thing happens. As you look at it, you can see an aperture, a physical aperture, and usually the electrical aperture is around 50% of that number if you need a number to do some rough calculations with. There are other antennas. We're going to talk about Yagis and LPAs later on, which are just effectively pieces of wire in three-dimensional space. And these things are sensitive in this direction. So if you look at them directly on, all you see is a thin piece of wire. These also have an electrical aperture that can be quite large and not really related to the physical aperture of the antenna. What we'll do is when you build a Yagi, you can calculate what the gain is, and then you go through that equation down here. If you know the gain, you can run it through this equation, and you can calculate the effective area of the antenna. So, so there's that.
I want to make a quick note. It says recording, but
Sure.
when I look in my Dropbox folder, I am not seeing a file being generated. It created a directory,
Yeah.
2 of them, but I don't know what's going on. So I'm not sure we're going to have a recording.
My words are lost to the ether then. So sad.
Might be hidden.
You want me to stop and you try it, or shall I just continue on?
I don't know. The only thing I can do is turn it off and start it again. I don't know what else to do. So why don't I try that?
Don't do that.
I'll press on.
No.
So this is just sort of a recap. So there's the aperture efficiency in some of these antennas. That's the horn antenna, parabolic dish. Some of them, like I say, you can see an aperture, and there's an aperture efficiency associated with them. Other antennas, we'll talk about all these tonight. There's Yagi antennas and log periodic antennas, dipoles. And it's not, no obvious physical aperture presents itself, but there is an electrical aperture that we can calculate. Okay, so I talked about gain of an antenna. Oops. And so what does that mean? Gain is typically something over something. And so the standard antenna that math starts with is an isotropic radiator. In other words, let me go to the next slide. I'll just put that up. It's a better one. So this is the standard isotropic radiator. This is the standard mathematical antenna that everybody uses. You dump power into the center of it. Power is spews all around equally in all directions in a sphere, and with no obvious preferential directions. And so this is the reference antenna. And you'll see the term 0 dBi, which is decibels below an isotropic antenna, or decibels related to an isotropic antenna. And so when you sit down in a quiet place and do the math with this thing and say, okay, I'm going to dump a certain amount of power into here. I'm going to back away a distance r. What's the power density on the surface of the sphere? When you do that, the power density at the surface of a sphere at distance r, it's just the power you dumped into it over the surface area of the sphere. And so this is the power density of the isotropic radiator, of an isotropic radiator to distance r. It's interesting to note it drops down by r squared. We might talk about that in a little bit. The effective area, when you do this concept and you go through the antenna math and say, well, I understand this from a transmitting perspective. What's the effective area of an isotropic antenna? This turns out to be what the effective area of an isotropic antenna is. So these are all our standard things, or standard standard antenna definitions. Go back one. So when we talk about gain of an antenna, we're talking about gain relative to this isotropic antenna. So if this is what the gain plot of that isotropic radiator looks like, which is by definition 0 dBi, the way an antenna gets gain is it can't add power to it because it's just a couple pieces of wire suspended in three-dimensional space. The way it gets gain is it emits energy preferentially in one direction at the expense of radiating energy in other directions. So in this particular case, in this antenna, it's radiating energy in this direction. It's radiating more energy in this direction, less energy in all the other places. And so you might think there's a relationship between if I take more and more power, if I took all this power and I just squirted it out here in sort of a 1 degree sort of beam width, that would be a high gain thing because most of the power would be shot into this direction. If I change colors, if I shot it out into, say, a larger width, let me do that again. If I shot it out into a larger beam width, I wouldn't throw as much power in any one particular direction. I still wouldn't throw a lot of power out in this area, but I would cover more angular space here. So the gain of this would be less, but the beam width would be wider. Does that concept sort of flow? And so because there's this relationship between beam width and gain, you can generate a couple rules of thumb. This is a rule of thumb. If you know the beam width of an antenna, if the beam width is 1 degree by 1 degree, this would be 1 squared, and then the gain of that would be 30,000, and then you could 10 log it and get a gain in get a gain in decibels. This table, you can generate a table. So if you have an antenna that's got, say, a 10 dBi gain, the beam width of that is 55 degrees. So that's about a kitchen funnel kind of angle. As you get higher and higher gains, which means you throw more and more power in one direction, the beam width gets smaller and smaller. So up here at 40 dB of antenna gain, the antenna beam width is only 1.7 degrees. So there's a good movie called The Dish, which is...
Yeah, I tried to find it. It's not available unless you're in Australia.
Oh, really?
On Netflix.
Oh, that's sad. Anyway.
I think you can order the DVD or the VHS tape or whatever it is.
So in 1969, they want to collect the video from the Apollo 11 mission landing on the moon. And I don't think this actually happened, but they have this antenna that is roughly 210 feet across. And the beam width of that turns out to be, or the gain of that turns out to be about 40 dB, and the beam width is about 1.7 degrees. At some point during the movie, again, I don't think this happened, is the power goes out in the receive station, and they can't, and then when they reboot the computer, the dish moves, so they don't know, if the Apollo is over here and the dish has moved, they don't know, they're not pointing at it anymore. And what's more, and also because the beam width is so narrow, they can't find it because they've only got this little window they can look through of 1.7 degrees. So part of the drama is they're trying to figure out which direction they need to point the antenna to be able to reacquire the lunar lander. And this is a classic search kind of problem. Is you have this antenna with this huge amount of gain, which means you can see signals that are very weak, but you can't see anything else around them. And so in the movie, what they finally figure out is it's heading for the moon. All they got to do is sweep around the moon, and then they find it. Not to be a spoiler, but it's a good movie about antennas, if you could believe such a thing exists. Let's see what's next. Okay, so that's antenna from a system level in a nutshell. So let's talk about some real antennas. And for the most part, a lot of it is just dipoles, and their array of dipoles. We talked about this last week, but we have to do some mathematical magic here to go on our journey. So why is that not? Okay, there it is. So the way we started this mathematically is we say, look, we're going to have a little tiny short piece of wire, and this is going to be much less than a wavelength, much less than our lambda over 20. But we're in mathemagic land, so we're allowed to do that. We're also going to let current arrive magically here. We're going to let it travel through this piece of wire, and then we're going to let it disappear on the other end. So this is all we're going to view. When we do that, and ask ourselves, what's the pattern of this antenna look like? How does it throw energy into the air? This is the kind of pattern we get. This is the they call these things a doublet. This is the doublet there, and so the pattern is this familiar donut pattern. So most of the energy gets thrown off broadside, and then nothing comes off the end. And I want to divert a little bit. This is the equation that describes this. This is the equation that describes exactly what this antenna is doing. And I don't put this here to intimidate or impress anybody, but I want to talk about, you'll hear the terms near field and far field on antennas. And we almost always exclusively talk about far field, but so whenever somebody does a plot like this, it's almost always far field. In fact, I don't think, unless you play around with antennas for a living, I don't think you'll ever run into near field stuff, but you'll hear the term. And so I want to be clear about what we're talking about here. So these are the magnetic fields, and these are the electrical fields. Near when you're in the near field of an antenna, and I'll explain why this is important in a second. When you're in the near field antenna of an antenna, R is very small. So over R big, but 1 over R squared is bigger. So when you're in the near field of an antenna, these terms with the squareds and the cubes are the ones that dominate the equation. When you're in the far field of the antenna, R is very big. So R squared is 1 over R squared is very small. So these terms are small. So when you're in the far field, these terms dominate. And I'll show you some GIFs later on. We'll talk about where the near fields and far fields are. The point being, so if you, again, sit down in a quiet place and look at these equations, in the far field, you don't have any energy coming off of, all the energy comes off broadside. None of the energy comes off here. When you look at these equations, you find that there's a huge electric field here and here. So there's a lot of energy that shows up here and high voltage. In fact, I have a story. A long time ago when I was a baby engineer, we built a system that had a 10-watt transmitter in it, and it was a monopole. So there's a piece of ground plane. Coming up through the ground plane, there was a piece of wire that was lambda over 4 long. And so it was late, 2 o'clock in the morning. I was sitting around waiting for the thing to transmit. It was a pulsed system, so I was waiting for the thing to transmit. And this antenna was wiggling back and forth, like a piece of wire might do. So I put my finger right here to just stop it from moving around. And when I did that, that's when it chose to fire. And I got this RF burn into my finger because of the high electric fields here. Another story is I used to deal with high voltage or high power transmitters, like megawatt kind of things. And we would transmit with a dipole, and the dipole looked like a dumbbell. Again, because there's such high electric fields at these points, if you didn't put these spheres on the end of the dipole, you would see corona come off the end of the dipoles, St. Elmo's fire kind of stuff. So the point being, there's even though you get these far field plots, there's a lot of other stuff going on when you're very close to the antenna that you may not realize. Okay.
Can you hear me, Kevin?
I can hear you.
Okay. Trying to think what works.
I can hear you.
Did I
Okay,
lose?
I was gonna just make a remark.
Can everybody hear me?
Can you hear me?
Can
Yeah.
everyone hear me?
We can
We
hear
can
you.
hear
Can you
both
hear
of you.
me, Kevin?
Okay, great. All right. All right, let's look at a dipole.
Kevin, can you hear Pete?
Say something, Pete. I cannot hear
Something.
Pete.
We heard
Okay,
him say something.
That's God talking. So,
Oh.
yep. Never mind. No
Can you
worries.
repeat what he said?
No
Or
worries.
is it a
It
question?
wasn't meant to be.
I hear sort of
I was just going to
way
say
down
that
deep
the
in the background. I
impedance,
hear
the
sort of
impedance on the end of the antenna
a
is
cadence
tremendously
associated
high.
with voice.
So that's why there's no power radiated.
He says that the impedance at the end
It
of the
doesn't matter.
antenna is very high, and that's why there's no power radiated.
It is. That's true. Yep. But there is a huge electric field there. I have some GIFs that'll show. He's still talking?
No, he's done.
Okay. I hear some sort of faraway cadence of voice, but anyway. So this is what you'll see for a dipole. Is its length is around lambda over 2. It's usually about 10% shorter, just because it works out better that way. There's capacitive effects that show up here and here, but it's usually, if you need to figure out the frequency of it, measure the distance, it's about lambda over 2. If you need to get closer than that, it's usually about 10% shorter than whatever frequency it's resonated at. And the way we model that is we take, we take measurements, or we do math, and we figure out what the current distribution is along the wire. And then we take all those doublets, and we assume that those things are all generated by those mathematically magic doublets that we had. And we do the calculus thing and integrate, and that's how we get the pattern of a dipole antenna. And this is typically what they look like. There's a connector on the end here. There's usually some sort of structure that converts the unbalanced coax into a balanced feed. And then there's wires that are just sitting out in three-dimensional space. This is what the pattern looks like. If this is our dipole, the doublet is in green here, and the dipole is in green, and the doublet is in blue. So it's the same sort of donut pattern with minor variations on it. They don't have to be a half wavelength. So if this is our dipole, and this is, again, our half wavelength dipole that we've looked at before, if we make it a full wave dipole, in other words, this distance is now a wavelength, we get a pattern that's similar, but it's throwing more energy broadside at the sacrifice of throwing some energy this way. If we do 3 half wavelengths dipole, we can get these sort of patterns out of it. So you can get different patterns out of them depending upon what you want to do with the antenna, or how you want to throw energy out. And let me put up some GIFs. All right, I'm gonna see if I can share a different window. Please stand by. All right, I'm going to share a different window. Wrong one. Okay, so gotta love the internet. So from a transmitting perspective, this is what the blue is the current distribution.
We see a blue thing with patterns going out of it. This
Perfect. Did you see this before, or did you see?
No.
No, we did not.
no,
Did you see that?
no.
Okay, so you
Yes,
saw that
this
one,
is-
right?
This is,
We saw this one.
you had just started
Okay.
on this one.
Okay, so this is from a transmitting perspective. This is what a dipole looks like. As you've got a signal source here, and it is forcing currents into the antenna. The blue is the current distribution, and the red is the voltage distribution across the whole thing. So, you know, there are times when the voltage just gets very high, and that's what I was talking about in the near field. From a receiving perspective, this is what this is how a dipole behaves. Is you've got this wave coming at the dipole. Back and forth at the resonant frequency inside the wire of the dipole, breaking there and bringing out the receiver down this way. So that's how it works in a receiving sense. The currents are the same, which is kind of feeds into that whole transmitter and receiver models are considered a little different, but they're identically they're the same thing. This is another picture of the same thing. So this is this is a transmitter, so it's being fed at the center here. There's you can see the power leaving the antenna this way broadside, and then if this had been expanded farther, you would see that there's nothing up and down on the side of this thing going that way. But you see the high electric fields coming off the end of it. And I find this just another picture of the same sort of thing. All right, so
those are the successive peaks radiating out of the antenna?
Yep, at the frequency you're operating. So each little pulse that comes out of there is one peak of the sine wave, you know, at 100 megahertz, whatever you happen to be operating at.
Cool.
Let's see.
And they're moving out at the speed of light through whatever medium that happens to be.
Exactly. If you're ham radio, some of the things we don't like about the dipole.
Kevin, you're cutting in and out.
It's if you have a 100 megahertz antenna. Okay. How's that? So if one of the things we don't like about the dipole is it's narrow band, so it's only about 10% of center frequency. So sometimes that's fine, sometimes not. So we're looking for ways to increase the bandwidth of the antenna. So it turns out one of the ways you can do that is you take a dipole and you fatten up the ends of it. Here and here. And this is called a biconical, or a bicon if you don't want to say the whole thing. And so the lower frequency is set by this distance. That's a half wavelength at the highest frequency. And this is a half wavelength at the lowest frequency. And so these are pretty common in screen rooms. If you're doing EMI tests, things like that, is you'll see these things all over the place because they're wide band. They have a nice stable pattern. They're a little cumbersome to deal with, but there's a modification we can make to alleviate some of those issues. But to do that, we have to talk about ground planes. So occasionally it's useful to put a piece of conductor near our antennas. And when we do that, if this is a mathematically perfect conductive piece of copper, so 0 ohms impedance, Turns out it behaves pretty much like a mirror. So if you have a dipole up here, and you observe this structure from far away, you can't tell the difference between this antenna and the ground plane, or two antennas positioned in a mirror image kind of aspect. One thing to note, this doesn't have to be a solid sheet of copper. It can be a mesh, as long as the holes in the mesh are less than our magic lambda over 20 numbers. So in your microwave oven, for example, you look at the window and you see the little tiny holes. Since those are a lot smaller than lambda over 20 at the 2.4 gigahertz frequency, that looks like a solid sheet of metal to the microwave energy inside. Structures, the holes in them for wind loading and other mechanical issues. If you want the weight, or again, get rid of wind loading, you can put holes in this thing, and as long as holes are small enough, it'll still look like a mirror.
Yeah, that's the Arecibo telescope.
So you take a folded piece of copper. I think the Arecibo telescope is a parabolic dish.
No, it's not a parabolic.
Circular parabolic dish. This is
it was spherical, I mean.
Right.
And it was all full of holes. I was there, actually. I took a bunch
it's
of
spherical
pictures of it.
Okay. Yeah, if you get the movie The Dish and you look at the dish in one of the situations, they have one part of the dish is solid, and then a larger part of the dish is made up of a mesh that, again, is there for wind loading. But since the holes in the mesh are so small, it still looks like a solid piece of conductor to the wavelength. So
that's what they told me at Arecibo when I was there.
Yeah. I wish I would have gotten there before it collapsed. So
I have pictures. I think it dates back to the late 80s when I was there.
Yeah. I remember there was a James Bond movie where he was running around the focal point of that thing.
Yeah.
So you can do things like this. Have you ever looked at a bathroom mirror? If you have a bathroom cabinet where the mirrors fold in and they can kind of fold against each other, you can do this kind of thing with antennas as well. So you put a dipole inside here, and it's got its current distribution. Here's the real dipole, and it will have three brothers that are just reflections. And again, when you're far away looking this way, you can't tell the difference between this structure and this structure. So this is a lot more convenient. This also has a nice effect of it brings down side lobes and back lobes. So there's a sheet of copper here. So any energy that does leave this antenna and hits the copper won't go through the copper. It'll just bounce right off again. We can use that for turning dipoles into monopoles. So this is very typical for car antennas. Is you take a piece of wire that is lambda over 4 long, put it through a sheet of copper. There's a mirror image dipole that shows up down here. And so from far away, this looks like a dipole. And so electrically, it's pretty much the same. And for our biconical, we do the same kind of thing. This is our biconical. If we replace the bottom part of it with a sheet of copper, we can get a mirror image in the copper, and we get this kind of antenna. And these are called disc cones. And this is pretty popular in the ham community because you could find these that are 20 megahertz to a gigahertz. And the pattern, again, looks like a dipole. And the frequency the lowest frequency set for the highest frequency is set by here and here being the highest frequency at lambda over 4. we talked about this last time, is you have an infinite, you cut a hole in it. That is length of that looks like a dipole in orthogonal direction at 90 degrees. And the microwave oven, this is the reason why you want the microwave oven to seal all around the edges, is because you don't want a slot antenna to let energy out. So if you get a piece of food or something in between the magnetic seal of the microwave oven and it causes a gap, there's an opportunity for energy to leak out there, and the opportunity increases as the length of this thing approaches lambda over 2 at the microwave oven frequency. So this is the kind of thing you see is there's a piece of waveguide here where you have a connector down here. She gets launched into this waveguide, and you see slot antennas. So there's a dipole looks this way, dipole this way. So there's an array of dipoles that generate the aggregate pattern of this slot antenna array. So let's talk about arrays for a little bit. So we've talked about dipoles to death. Most of the antennas, or all the antennas, have to do with, we want to arrange radiators in three-dimensional space to enhance the patterns or get characteristics we're interested in. So again, back to Mathemagic land, we're going to put in n we're going to separate them by known distances, and we're going to magically feed them with signals whose end vary and whose phase we can vary. And we're going to just run some MATLAB plots to see what kind of characteristics we can get out of this thing. So broadside looking out of this thing is going to be 0 degrees, and then as then this is stay broad. So here's what we get if we have this. So mathematically, we're going to do a simple analysis. We're going to have these isotropic radiators, omnidirectional radiators, separated by known distances, and we're going to be able to feed them, because we're doing Mathemagic here. We're going to be able to adjust the phase and the amplitude of all the signals that we feed into these things. And then we want to look at what this array does when it's just got omnidirectional radiators in it. And so that's what we're going to do now. And so the MATLAB plots that show up, these aren't dipoles. I just put the line there because I wanted to emphasize where radiators were. So here's two radiators. One's right here and one's right here. So they're separated by both at 0 degrees. And so it looks like in that situation, so you can get a nice cardioid pattern out of it. So microphones and things do that. A lot of amps do that. If we feed them by 180 degrees, this is the pattern we get. And if we feed them at 270 degrees, this is the pattern we get. We can change it around. We can rate it by half a wavelength. And again, 0, 90, 180, and 270. So we can get these different patterns from our isotropic radiators, or omnidirectional radiators. If we can figure out a way to feed them at the right at different amplitudes and different phases. So on the other side of this is we're not gonna you can't really build isotropic radiators that are any good except for real precise. How can we arrange those to get patterns and characteristics that we like? How can we increase the bandwidth? How can we make the gain get higher? All those questions we want to ask. So this is the road we're trying to travel right now. It turns out that if you have an individual radiators that look like this, and you have an array pattern that looks like that when you put in omnidirectional radiators, then when you multiply the two together, that turns out to be the pattern of the array when you've got real antennas in it. So you take your individual radiators, multiply it by they call this the array factor, and that gives you the pattern of the array with realizable antennas in it.
You're doing FFTs and inverted FFTs?
You can. That's another way to do it. So this is the kind of thing you see in GIF land. So same kind of thing is we've got these radiators. We're changing the phase and amplitude of all these radiators, and depending upon how we set it, we can get energy to go out this way. And you might imagine that if we change the phase and amplitude of these things, you can get the energy to go out pretty much any direction you like. This is another example. So here we have our radiators arranged in arrangement, and we can get all energy to line up so that the energy ends up directed out in a direction like that. Those are the only two I had. All right, let me do one more. So here's another graphic of array factor. So you can see, if you look closely, you can see the elements in here. And we're just changing the relative phase difference between all these different ones. And you can see the patterns are changing. You see the patterns are plotted here and where most of the energy is going. So stop sharing, share again. All right, getting better at this. Okay, so we know what a dipole looks like, and we've got some idea of how the array factor works. So when you look at these two antennas, or all these antennas, so this is a log periodic array, and you can see dipoles happening here and here, and then there's ones that are smaller here and here. So you get a sense of, since you look at this thing and you see that they're of different lengths, you might get the feeling that this is a, and the highest frequency would be set by these little baby guys down here being lambda over 2, and the lowest frequency would be set by this distance being lambda over 2. And all those assumptions are about correct. So if somebody hands you, if you look at this antenna and somebody wants to know the frequency range of it, you can say that you can measure this, you can measure that, and to a rough guess, 10% world, you'll be that's the frequency. So these are log periodic antennas. They're fairly common. You used to see these TV antennas a lot. The second most common antenna we'll deal with is this guy, and this is called Yagi, sometimes called Yagi Uda.
Your video is cut out.
And again, looking at this, dipoles array, and some of these dipoles are about the same length. You might guess that this is a narrowband antenna, and that's lambda over 2, and you would again be pretty much correct. Question we have dipoles. We're going to assume they radiate at some amplitude. Once we know what amplitude and phase these things are all radiating at, we can go through our array factor and we can figure out what these antennas are doing. So that's how you do it in the mathematical world. We're not going to do that. I'm just going to tell you what the answers are. We'll talk about the Yagi. We have all these dipoles. They have to be electrically connected. So this is the only element that gets driven element called the reflector, and that's usually a little bit longer than the driven element. And then there's as many of these, they call these the reflectors. No, directors, I'm sorry. They call these directors. And I used to run a lab class, and we would build antennas. And one of the ways we would build antennas is you would take corrugated cardboard, that's got that corrugated paper in there, take pieces of coat hanger wire and just slide them in to various places. And so if you look at the top of the cardboard, you would have the driven element right here. The directors would be here, just again, slid to the side of the cardboard and positioned appropriately. And then the reflector would be back here. But the point being is they don't have to be electrically connected. This whole thing, this is just structure. And this can be PVC pipe, it can be metal. It doesn't matter. It's just structure. And so looking at what we've got here is we've got these dipoles. They're separated by a distance, and this is usually about lambda over 5. One of the things that RF people talk about at cocktail parties and stuff is how far apart do these want to be? They're usually about lambda over 5, but they can vary. And what distance or what length do these things have to be? And so there's a relationship, and people do PhD theses on how long can this be, and where do these get positioned in 3-dimensional space to get a particular characteristic out of the things. But to a first cut, lambda over 5 and lambda over 2 is the numbers that show up. Anything I want to say about that? So there's a driven element. So your coax would go right into this guy right here. And there's usually some sort of matching circuit back here that takes care of converting balance to unbalance and things like that. But this is the only element that gets driven. And so what happens is you shoot energy into this this element right here, and it begins to radiate. And so the energy transitions, do that. So some of the energy couples into this because it's close. And so from a transmitting perspective, so energy ends up, you drive this element and it begins to radiate. It begins to resonate and throw energy into 3-dimensional space. This element, because it's so close, it picks up the energy and begins along this. They're at a different phase, physically removed from this element. So lambda over 5 kind of numbers. Same thing with here is this element begins to radiate as well with a phase delay, and because it's a different length, that also the reflector radiates that. It's to fill up with this mechanism of coupling between elements repeats itself, and so this whole array begins to fill up with energy. And now we have all these energy dipoles. They're radiating at with different phases at the same frequency. Throw energy out. All the others start to constructively interfere with each other, and energy throws out the front. And I have some GIFs. This almost never. Oh, God. All right. Can you see that one? You guys there?
Yes, I can see it.
Yep.
Okay, there we go.
It's a little bit
here's the driven element. Okay, here's the driven element, and you can see is the following elements, and once they all get radiating, it emits energy out the front end here. Let me switch to another one. This is one with only 2 elements. The same kind of thing is happening. Here it's driven. We see energy coupling between the two, but you don't really see the energy coming out the front of it. And let me do the GIFs. Oh, all right. State is there's the driven element. All these, again, all the dipoles begin to radiate. Because of the way they're arranged, no energy goes out the back, or only a little bit of energy goes out the back, and most of the energy gets directed out of the front. Here's a different viewpoint of the same thing. So there's a driven element, there's a reflector. These are the 2 directors. And when you carefully look at where all the sine waves are, you see the ones coming out the front are adding constructively, and the ones coming out the back are adding destructively. Same deal. And this is what the current distribution looks like on all of these antennas by the get radiating and are all in steady state. So there's a driven element, and so again, you get all the dipoles radiating. All right, let's go back to the other one.
Each of the elements in the Yagi array is effectively changing the impedance of the driven element. So it's reflecting back into the driven element too.
But it's not something, unless you're an antenna designer, it's not something you worry about. Mostly what you get is somebody's worried about that, and it's place the elements appropriate so that by the time you look into the whole thing, you see whatever. Where were we? All right, showing. I think I showed you all the GIFs. So we'll press the LPAs. So antenna, and we talked about this. This determines the highest frequency. This determines the lowest frequency. This is how it's driven. And it turns out that if you put a signal into this antenna at a frequency such that this is about lambda over 2, then these are the elements that participate in the radiation. So you have a longer one, one in the middle, and a shorter one. So you might be able to convince yourself that that looks like a 3-element Yagi. So that would be the reflector. That would be the driven element, and except they're connected. Well, the reason I bring that up is because it turns out that this is sort of what happens: is the energy will find a place to the lambda over 2 area of the antenna, and that's where it'll radiate from. And its gain is such that it looks like about a 3-element Yagi. So its gain is about 6 dB or so, but it's really wide band. That's the lower frequency, or I'm sorry, that's the highest frequency, and that's the lower frequency right there. And also, this is the way they're typically drawn. If you see them in the field, it's not quite obvious that this is the connection that they make. So, for example, if you look at this antenna here, there's a feed here. Some of the elements are on the bottom, some of the elements are on the top, and if you trace out the coax goes along the lower element here and touches some of these elements, and then when it flips up, as it travels back along this way, it touches the other elements. The net result is this sort of architecture where these are driven in the same phases as they would be if you connected them up this way. But somebody spent a period of time figuring out how to make this thing just mechanically work like this, because it's a lot more convenient to drive it back here and then have a coax go up here. And mechanically, this is a lot friendlier solution than the one at the bottom is. So that's the deal with that. That's not a very good one. That's not a very good one. So there's the current distribution. So as this thing moves along, so 18, 20, I'll stop it when it gets back to well, I've stopped it here at 33 megahertz. So this is the, these are the elements that are radiating at 33 megahertz right here. And you can see the current distributions on these. Mostly the ones that are participating in the radiation pattern. This is the one behind, the one in the middle at 33 megahertz, and the one in front of it. And so, like I say, it ends up being about a 3-element Yagi, pushing energy out the front as we, whoops.
So that changes when you change your transmitting frequency?
Yeah. It radiates. It looks like it radiating from different points. So here's what the antenna looks like at 12 megahertz. Here's the current distribution. And so since this element here is lambda over 2 at 12 megahertz, this is the one that has the highest current distribution. And so for the most part, I guess this element, these 4 elements are participating in the radiation pattern. The rest of them are fairly flat. They don't have a lot of current being induced in them because they're not at resonance. And so that's how the antenna works. I have another story. At the same time, when I was dealing with high power stuff, I accidentally hooked up. You can build these antennas out of a printed circuit board. So let me go back to the drawing thing. Draw a picture. I needed. So you can build these antennas. And the system I was working on had it had a high power transmitter. This particular one was 1,000 watts, and so that's one of the ones we used, the dipole that had the 2 balls in the end of it to keep the corona down. The receiving antenna was a log periodic antenna that was just on a printed circuit board, and so it would have and I accidentally traded the wire that went to the high power feed. I antenna right here. I threw the switch, and you hear a smoke puff go into the room, and there was a scorch mark on the antenna right at the place where the lambda over 2 power, where the antenna was radiating. There was so much power there that it scorched the board, but it only scorched the board in the place where the elements were radiating. Okay, so, and we talk about, again, this is, by now it starts to get boring. It's because you start to see the same thing over and over again. You start to see just dipoles all over the place, and you start to see them in arrays. And for most garden variety antennas, it's dipoles in arrays is sort of what you see. Next time you go to a ham fest, wander around, and you can start to identify antennas that just being dipoles.
So those slots are offset from each other?
Let me get back. This
is the spacing between the slots important, and why are they staggered like that?
So it's dipoles in an array, and if you look at the center of that, if you look this way into the waveguide, the energy distribution in the waveguide looks like that. It's 0 at the walls, and then it's higher in the center. And if you put a slot here, effectively what that's doing is changing the amount of power that slot sees. And so they're all seeing about the same amount of power because they're all offset from the center about the same amount. The distance between them is a measure of the phase difference between each slot. So as the signal propagates past this slot, it starts to radiate at whatever phase this is, but then it has to experience another phase shift before it hits this slot. And so this slot radiates with the same amplitude, but a different phase. And that idea continues as we move along these antennas, or move along the waveguide. And this was the transmission lines, and I suspect this is just a piece of copper, just a short circuit. So energy, like we talked about transmission lines last time, energy reflects off this end and comes back this way. And so if you do antennas for a long time, I know people who can see fields, and they can look at this and they can tell you in excruciating detail what's happening and how the amplitudes of the incident and reflected waves are adding up so long. I mean, I can look at it as in a sort of I don't. Does that make sense? So each of these slots gets radiated. It radiates at a slightly different phase depending upon the distance between the two.
Yep.
Yeah. It's a phase thing. If this slot were offset farther, if these sets of slots were offset farther over here, they would be experiencing this field right here. So
Right.
they'd be lower power, exactly. And so that's how you can change the amplitude between the two. So let's talk about parabolic. We'll talk about parabolas and then horns, and then we're done with it. Then we'll be done with this whole thing. So parabolic dish. This surface here isn't frequency selective, except that it has to be accurate. Our friend lambda over 20. The only thing that determines the frequency that this thing radiates at is what goes in here. There's a dipole or some frequency selective element that lives inside at the focus of the parabola. And as long as this parabola is parabolic to whatever tolerance we like, this is the only frequency selective element in the device. And so here's a parabola. So if we're at the parabola focus, energy leaves our isotropic radiator and transmits out, and all the waves leave the antenna in parallel. If we're off focus, either too close or too far away from focus, it does nothing but make the beam wider. So in this case, you get that widening. In this case, you get a widening. They end up crossing out here somewhere, and they end up again being just wider. There's a couple of relationships that if you flip through ham radio books or antenna books, given the diameter of the dish and the wavelength, you can figure out what the gain of the antenna is based upon the aperture efficiency. Again, 50% if you got to pick a number. The diameter of the dish and the wavelength you're operating at. So all these rules of thumb come about through these equations. And there's a rough one. The bandwidth, the 3 dB beam width is about 70 degrees. The diameter of the dish in wavelengths. Rules of thumb that pop up that given the diameter of this dish and the frequency you're operating at, you can fit characteristics of the dish. I'll try one more. Stop sharing. I have a kind of a cool GIF. It's one of my favorites. All right, let's see if I can stop. Let's see if I can share this. The focus is right there. And as this thing emits a pulse, stand by. It strikes the dish. If the dish is parabolic, energy goes out this way. Notice we've got this guy out front. We don't like that. It's not part of what we want. So very often we'll put some sort of structure here to suppress the energy coming off the feed so that it eats flat to the dish. As I've been saying, you also see, if you look closely at the you also see energy curling back behind the dish. And that's one of the causes of parabolic side lobes, back lobes. As the energy encounters this edge, it refracts off of it. So one of the things people do, which is a contributor to that aperture efficiency, is they don't radiate or illuminate the full dish, is they'll actually put an antenna here that's got gain, so when you get to the edge of the dish, you're not radiating it very strongly at all. And so that keeps the side lobes and the back lobes down. And there's a lot of art associated with, well, how do you things with the feed and the edge of the dish, so, back lobes and side lobes. Structures here whose purpose is fact, a lot of the real sophisticated radar, like in war, they'll have other antennas, other parabolic dishes at the top and the bottom or around the dish, whose job it is to do nothing but suppress side lobes. All right, let's go back to the. So we had the dish. Can you guys hear me now?
Yeah.
Yep.
Okay, so we had the dish, and this was an omni radiator. So you would see waves coming off this omni radiator that would strike the dish. And because this is a parabolic dish, we would end up with all the energy floating out, coming out this way. And some of the energy would strike the edge of this dish and refract off of it. And that was what would create back lobes and side lobes on the dish. And I was saying that they, on more sophisticated dishes, you'll often see structures placed on the outside of the dish that look like clover leaves, whose job it is to dissipate energy to keep it from folding around the dish. So one of the reasons why you care about this is, so if you're, let's say you've got a radar and you're looking at an enemy plane and your beam width looks like that, the only way that you know where your target is as this dish rotates around, the beam sweeps across the airplane. And so when you get a peek out of it, if you assume you know what your antenna is about, then you tell that, okay, the plane is in the direction where I get the maximum signal. But if you're a bad guy, let's say you're in this plane and you want to confuse this radar system, and your dish has side lobes on it. As you're sitting here, you can actually measure the pattern of this guy's dish as he rotates around, because you'll see strong pulses as he rotates past you. You'll see energy from this side lobe, from the back lobe. And then if you want to get real sophisticated, when you receive a pulse from him, you can send out a pulse time so that by the time the antenna is pointed this way, it's going into the side lobe. And so he'll think that you're over here somewhere when you're actually right here, but you're doing active jamming on him. Does that make sense? So if you know the antenna pattern and you can measure the antenna pattern, the side lobes can actually give you a way to confuse the radar operator and tell him you're at a different place than he thinks you are. So that's why side lobe suppression is so important in more sophisticated dishes, is because people want to, they know about that technique and they want to mitigate it.
That's when they're receiving, right? When they're transmitting, by suppressing that, does that cause more power to go out the main lobe, or?
No, so let's say you're just sitting here watching the signal coming from the radar station. So as he sweeps around you, you can actually measure his pattern, because you'll see when he's pointed at you, you'll see strong pulses, and then you'll actually be able to see his side lobes, because you'll see power coming at you, but it'll be a lot lower.
Right.
So the problem he has a two-way path loss he has to deal with. So he has to send power out and then get power back. So he has a two-way path loss. If you decide to transmit at him, you only have a one-way path loss. So what you can do is you can measure his dish, you can figure out how fast he's rotating. And then when you see at the right time, you can transmit a pulse at the same frequency so that it lands in one of his side lobes. So he'll be pointing.
Yeah, I understand that one.
Okay.
In the previous one where you're talking about the cloverleaf things along the edges,
right?
Is by minimizing what goes out the back, does that maximize what goes out the front?
So by the time the power, you talk about these powers, you're down pretty low. So you may be transmitting 100 watts out here. There may be 10 milliwatts. It's floating around, coming around the back of the antenna. So it's not a power thing. You just want to kill the sensitivity of the dish to directions that you don't intend to receive from. So you can throw away the power. You can actually put lossy things here, or if you're real clever, you'll put another antenna here. You can put a dish here whose job it is to do nothing but suppress side lobes. Again, it gets real sophisticated.
Yeah. I'm just trying to understand whether it's to prevent people on the other side from seeing radiation that you don't want them to see, because you're interfering with what they're doing, or whether it's
Well, so this is one case, is the radar case. There's another case, the Arecibo case, where remember you've got this antenna that's pointed up at a cold sky with 2.7 Kelvin. If down here is the warm Earth at 290 degrees Kelvin, if this antenna has side lobes and you allow energy to leak around the side of this thing, you can see significant. Most of the noise this antenna sees, if you're not careful, will come from the warm Earth sneaking around the side lobes and the back lobes of the antenna. So that at Arecibo, they also worry about suppressing side lobes because they want to keep the warm Earth from getting into their feed. Does that make sense? So
I think so.
The noise out here is so low that the noise from the warm Earth, which is in the back of the antenna, the power can actually sneak around through this side lobe effect and get into the feed. And so if you're not careful, the majority of the noise that you see on the receiver will be due to this back lobe noise coming in around the side of the antenna.
Yep.
So, and it depends on the numbers. So this is very cold and this is really reasonably warm. So when you sit down and do the math, you can figure out how much side lobe suppression do I need on this antenna before the noise that I'm seeing is mostly coming from the galactic center and not from the Earth right behind me. And finally, the last thing we'll talk about is horn antennas, and it's the same kind of thing as parabolic dishes. You have an aperture here. There are whole bunches of equations that tell you, given this aperture and the wavelength, what the gain of the horn is going to be. You'll often see structures inside the horn whose job it is to make the horn wider bandwidth or to suppress side lobes. There's all sorts of structures in there that people worry about this sort of thing. You can get PhD theses on it. Okay, that's really all I had to say about antennas. Any questions?
So if you have a Yagi antenna or something that you're transmitting on,
Yes.
it also will receive that same frequency coming from the direction you're transmitting on, right?
Yes.
And that will somehow interfere with the signal you're trying to send out somehow.
So,
Is that a problem or?
well, so normally when you operate antennas, you either operate them in a receive mode or a transmitting mode. Occasionally you'll see switches where people will switch back and forth, or they'll use the same antenna for transmit and receive at the same time, but that's a hard problem. The transmitting models and the receiving models are good for understanding the antenna, but very often you don't use the same antenna to transmit and receive.
So for the radar, do they use the same antenna? Or do
For the radar, they do, but they can spend tons of money to, it's aircraft radar or it's the military, so they can spend a ton of money and switch and all sorts of things. Like there's a lot of problems associated with transmitting and receiving on the same antenna, so people try not to do that.
It's also just a pulse rather than continuous waveform.
It can be a continuous waveform. And a lot of times they'll transmit on an antenna that's completely removed. Airports do this a lot. There'll be a transmitting antenna out in a field somewhere, and if you know where that is, and you can just use the rotating dish to be a receive antenna, and then that solves a lot of your problems, makes the system more reliable and a lot cheaper. So they don't have to be at the same place. Anybody got any other questions? Oh, that was 2 hours.
I have questions, but they would take another 2 hours. They get into polarization and how that behaves.
Yeah, I skipped a lot of that stuff just because it was all. I mean, this is normally a 2 or 3 lecture thing, so I skipped a lot of that stuff.
So the linear phased array antenna.
Mhm.
Oh, it is a dipole. So there's one connected to the green and one connected to the red, and they act as a dipole. Okay. I was thinking that they were like monopoles, only connected at one end, but they are.
Right. Well, and also remember, a monopole is just a dipole with a copper sheet as a mirror. So it's from a pattern perspective, it's mostly a dipole. It's funny as you start to look at them, you can start to see all the similarities, and a lot of times it just boils down to dipoles.
So is that structure in the middle acting as the reflector?
Which I'm not sure what picture you're looking at.
Just your linear phased array where it's zigzaggy elements.
Oh, the log periodic antenna.
Yeah.
Right.
I'm sorry.
Yeah. What was your question?
Originally, it was are those really dipoles or are they monopoles? But
They're
they're dipoles. One is connected to green, one's connected to red.
Right.
It's just that they zigzag the polarity of them.
Right. And that's the simplified schematic diagram. When you look at one for real, it's not intuitively obvious that that's what they're doing, because they're trying to solve a lot of mechanical issues at the same time. But when you unfold all the electrical connections, that's actually what's happening inside the antennas.
Yeah.
The
ordering the elements is probably different, but which changes the phasing as it goes by and things. But
yeah, and it doesn't matter if you need to switch by, or if you need the phase to change by lambda over 5, you can change it by lambda over 5 plus 360 degrees, and it's still the same phase shift. And so you'll see a lot of that kind of thing happening.
Yeah. Okay.
All right. Well, thank you all very much for your patience and trying to get this to go.
Thanks a lot, Kevin.
My pleasure.